Okay, we're going to continue on here, wrap up chapter 12, which should be the bonding. Then we're going to roll into back to chapter 5, do some of the naming, and then we're going to roll out of here, I think, and go to my next class. All right, so last time we talked about Lewis structures, and we talked about really the steps that you want to follow when you're drawing Lewis structures for covalent bonding. And remember that it's really important to follow those steps so that you do end up with sort of the correct structure when it's all done. You want to think about logical arrangement of how the things put together. Remember that the least electronegative atom is typically in the center. A lot of times everything else is attached to the guy in the center, but we can't have multiple central atoms like we had with the nitric acid I think we drew. The most important thing, right, is to figure out the total number of valence electrons that you have. Remember that if you're drawing something with a charge, you need to adjust your count. So if something has a negative charge, then you need to add those electrons in. If something has a positive charge, then you need to subtract those electrons. Once you have those number of valence electrons, that is the number of valence electrons your picture needs to have. You want to go through by just making, again, a single bond between the central atom and all the outside atoms. That will use up a certain number of electrons. Each line represents 2 electrons. All the remaining electrons go on as pairs on the outside atoms until they do have 8 valence electrons. If at the point like here we maybe filled up all the outside atoms but still have electrons to put on, then that's where we should go to the center atom and lay up some pairs of electrons. At that point, once you hit the center atom, you should not have any more electrons to put on your picture. And it's at that point where you put on all your electrons that if you have not met the octet rule, that is where you want to try to fix it. So in this case, if everything meets the octet rule, which it does, then we're good to go. We don't really have to do anything to it. Everything's fine and we have the right picture. But if we kind of roll through this here and we ended up with something like this, that guy in the middle there would be short electrons. And we would need to make a double bond, for example, to try to fix it. Again, a reminder that when you make like a double bond, we're going to bring a pair of electrons in to do that. And we would end up with something that looks like this in this example. And now that guy in the middle is fine. Remember that you sort of want to use up all your double bond options if necessary. If that still doesn't fix it, then you want to go to a triple bond, which is done the same way. You're just going to bring another pair of electrons in to make that triple bond. Any questions on drawing those Lewis structures? As I talked about before, you don't really typically want a double bond or triple bond right out of the box. You do want to kind of save it to fix something that's incorrect. At the end there, we talked about some exceptions to the octet rule, although everything that we draw in here will obey the octet rule. Reminder that you can have an incomplete octet. That is typically boron is typically the guy that can do that. That is somebody that's fine with less than 8 electrons. You could have an odd number of electrons, which means somebody has an unpaired electron, just one individual leftover electron. And the most common sort of exception to the octet rule is the expanded octet, which is when you can go more than 8. And that is on the periodic table where sulfur is to the right, to the left, and down. As we talked about last time, they have basically extra spots or orbitals, which are their d orbitals, to house all the extra electrons. So they're able to go over those 8 electrons. That's also why we talked about last time as well, things in the period before it, like carbon, nitrogen, oxygen, they cannot go over 8 because they don't have those extra orbitals available to them. So they have nowhere to put those extra electrons. So they must obey the octet rule. A reminder that we will not draw anything that is not going to obey the octet rule in this class. We'll save it for when you go to 1A. You could draw all kinds of expanded octets, and you'll do a ton of those. Any questions on any of the Lewis structures, drawing the structures, or anything like that? All right. All right, so the last thing we're going to talk about, or one of the last things we're going to talk about in this chapter is molecular geometry. And molecular geometry is basically the 3-dimensional structure of these molecules. based on the number of electron pairs there are, how many bonds are going on, and really what type of electrons are present in these molecules. So we can make a fairly good prediction of the geometry based on the Lewis structure, but not really the whole Lewis structure. It really comes down to the central atom. And when you do geometry, it's always about the central atom and the atom there in the middle, when there is a central atom. And that is really the most important thing to look at in your Lewis structure when you're trying to assign geometry. And it really boils down to looking at two things when you look at the central atom. And these are the two things that we're going to look at, which is the number of electron pairs there are around that central atom. And those could be dots, those could be lines, it doesn't matter. It's just the total number of electron pairs you got going on and the total number of bonds. So these are really, for the most part, the two most important things that you want to look at when you're trying to assign geometry to a molecule. Most of us, myself included, can't really visualize three-dimensional pictures in their head of how everything is moving around and stuff like that. So it really does come down to, really with this stuff, to memorize the names that go with these combinations of electron pairs and bonds. So like 2 electron pairs, 2 bonds is linear, and just to know it that way is probably the best way to sort of learn the geometry. So the basis of this geometry is the idea that, frankly, bonding all involves electrons. So at some point along the way, we're going to have electrons near each other. And since electrons are negatively charged, and when we get two negative things near each other, they really don't want to be near each other, right? They are going to repel one another. So what happens is, as these electrons try to move away from each other, bonded atoms and stuff also start to move as they move, and it affects the geometry of the molecule. And we get different geometries based on how successful they can be trying to get as far apart as they can from each other. They obviously can't escape because they're being shared in a bond, but they will continue to move away from each other as far as possible to sort of maximize the space between them. And this is going to give us really the rise of our different geometries that we see. The name of this is what is known as valence shell electron pair repulsion model, also known as VSEPR, which is why the abbreviation is there. And it is really based on the central atom, how many electron pairs and how many bonds there are. It's basically broken up into two different categories. One where you draw your Lewis structure and you have no lone pairs or no bonded, non-bonding electrons on the central atom. So basically, when you draw your Lewis structure, there's no dots. Yeah, so on that central atom, there's no dots on it. And there are ones where we do have lone pairs on the central atom. So you draw your central atom and maybe you got some dots happening there. And because of the non-bonding electrons being present, that means that there is not an extra bond there. There's not an extra atom staying there. And that allows the geometry to also change a lot more. So there's two really important sort of considerations when we do geometry, and only when we do geometry. And the really important one is actually the first one here. When you look at your Lewis structure and you go to that central atom and you're counting up the number of electron pairs and the number of bonds, if you have a double bond or a triple bond, they both count as 1 electron pair and 1 bond only. So effectively, in terms of geometry, a single bond, a double bond, a triple bond, doesn't matter. They all essentially count as 1. And they also count as 1 electron pair. So when you're doing geometry, that's a really important consideration. The second thing there is about those resonance structures that we drew the other day. Remember that you could draw more than one structure if you have options as to where you could put the double bond, and you could apply this geometry to each of the resonance structures. And in most cases, the resonance structures, no matter which one you do it for, will give you the same geometry, no matter which one you kind of look at. So it'll be the same. But the most important thing really is double bonds, triple bonds. One electron pair accounts for, and one bond. So let's take a look at really the simplest type of geometry that you could have. And if you don't like the X's and the A's, don't even worry about it. But the simplest geometry you could have comes about with our diatomic molecules. And because the diatomic molecules only have two atoms involved, so like our H2, our F2, our O2, our HF, our N2, no matter what it is, it doesn't matter if it is two of the same elements, two different elements, it's got a single bond, a double bond, a triple bond. In terms of geometry, the old saying is the shortest distance between 2 points is a straight line. And if you only have two atoms, the only way you could arrange them is basically a straight line. So the geometry for something that is diatomic will always be linear. So it's basically a straight line. And again, that's the only way you could put two things together is no matter how you do it, it's just a straight line between the two. So as soon as you see two things, a diatomic molecule, and you want the geometry, lay up linear, move on with your life, it'll be okay. Yeah, so single bond, double bond, triple bond doesn't matter again in this situation. Now, if everything was that easy, that would be great, but of course it's not going to be. So when we get to three or more atoms, we do have to look at a couple of things to decide sort of the geometry of what is happening. So let's take a look at some of these here. So these are three or more atoms involved. And once again, we're going to talk about, by the way, before we get started, I guess, too far, we're going to talk about really two types of names. And one type of geometry name is what is sometimes referred to as the electron pair geometry. And for our lecture here, I'm just going to abbreviate that as like EP per electron pair geometry name. And that describes the geometry of all the electrons around the central atom, how they're sort of arranged in three-dimensional space. The other geometry name that we're going to talk about is the molecular geometry name. And this is sometimes also just referred to as the shape, like on your lab or activity there. I think it's just a shape. And that is what is referring to the molecular geometry name. For our purposes here for our lecture, I'm just going to call it MG, so I don't have to write it out all the time. And these are two different names that describe the geometry of the electrons, which is the electron pair geometry, and the molecular geometry describes, as a result of the types of bonds that you have, the types of electrons that are present, what the actual overall shape of the molecule is, and as the things start to move. So in certain cases, the electron pair geometry name and the molecular geometry name will be the exact same name for a certain situation. Now, in other situations, you will have an electron pair geometry name and a different molecular geometry name. And we're going to talk about why those names change as we go through it. But in certain cases, they'll be the same. And in other cases, you'll have some different names for some different situations. So let's take a look at these and sort of see what we're talking about here. So this is beryllium chloride, and this is an exception to the octet rule. It's an incomplete octet. Remember that when we do geometry, that is the only one that you should be concerned with. Shouldn't be concerned with any of the outside atoms or anything like that. It is always the central atom when you have three or more atoms. And this is really the two things that you want to look at. You want to look at the number of electron pairs and the number of bonds. Now, when we count the number of electron pairs, it doesn't matter if they're dots, doesn't matter if they're lines, doesn't matter if there's single bonds, double bonds, all those things. It doesn't matter. We just count them as electron pairs. So in this case, we have one electron pair there and two electron pairs there. By the way, the total number of electron pairs, like we're counting in this geometry as we go through it, is also what they refer to as steric number on your activity. Yeah? So when they say steric number, that is what they're referring to, the total number of electron pairs there are around the central atom. Now, the other thing we want to know is how many bonds there are, and that's one bond and two bonds. So the electron pair geometry name is based off of how many electron pairs there are. And in this particular case, that electron pair geometry name is known as being linear. What's going to happen is, frankly, these bonding electrons are going to go, I do not want to be near you. I'm going this way. I'm going to go this way. And as far apart as they could get from each other is opposite ends of a straight line. It's because there's two bonded atoms. So you can get to opposite ends of a straight line. And that means something with two electron pairs and two bonds, the molecular geometry or shape would also be known as being linear. So linear is both the electron pair geometry name in this case, and also the molecular geometry name or the shape of the molecule. It is as far away as those two bonded atoms can get, 180 degrees apart. You do need to know the bond angles. They do want you to know that in this class. So the bond angle there is 180 degrees. And the reason why both of these names are the same is because the only type of electrons we have here are bonding electrons. So as those bonding electrons start to move away from each other, they're hanging on to the atoms. So the atoms move the exact same way as those bonding electrons. So where those bonding electrons end up, so do the atoms. And the shape of the molecule reflects the same shape that you see with your electron pairs. And that's why we have basically the exact same name for both of them. Any questions on that there? All right, the next sort of geometry will be something like this, also an incomplete octet. And this is, when we look at it, number of electron pairs, which once again is the central atom we're looking at. So that is 1, 2, and 3 electron pairs. The number of bonds in this case, 1, 2, and 3. So once again, the electron pair geometry name is based on the number of electron pairs. In this case, we actually have 3 electron pairs, which means as they start moving away from each other, they can't go as far away as 2 because they got the 3rd electron pair in the way. So they got to kind of shift around a little bit. And they shift around to a geometry known as trigonal planar. And sometimes people will call this triangular. The molecular geometry in this case, when we have 3 electron pairs and 3 bonds, is, as I mentioned before, basically what's happening in this situation is as this electron moves this way, the other electron's moving this way. But what happens because of that 3rd sort of electron pair, those two can't get too close to each other. So they kind of swing out into the corner here, basically, of a triangle, which is why the molecular geometry name is also going to be trigonal planar or triangular. And it's really because they end up in the corner of an equilateral triangle, basically. And that's as far away as they can get from each other, because now instead of only 2 things being there, we now have 3 things, and they all got to keep sort of their distance from one another. And it has a bond angle of 120 degrees in this case. So in this case, same deal. We have the same electron pair geometry name and molecular geometry name because the only type of electrons we have here are bonding electrons. So once again, as those bonding electrons move, so do the atoms move the exact same way, and they end up with the exact same geometry in both situations. Any questions on that one there? The next example is something where we got 4 things attached to a central atom. And in this case, once again, it is that central atom we want to look at. And we want our number of electron pairs. And that is 1 electron pair, 2 electron pairs, 3 electron pairs, and 4 electron pairs. Number of bonds in this case going to be 1, 2, 3, and 4. Once again, something with 4 electron pairs. Electron pair geometry is going to be something known as tetrahedral. We have a similar situation. We got these guys trying to get away from each other. We got these guys trying to get away from each other. These guys got to keep some distance. And frankly, these 2 guys also has got to keep some distance as well. And we do get a molecular geometry name of tetrahedral as well in this case. Again, both the electron pair geometry and molecular geometry name are exactly the same because we have only one type of electrons here as well, which are bonding electrons. So once again, as those bonds, the electrons move, so do the atoms, and they end up in the same geometry. As you can see, it's getting a little bit more crowded in there with 4 things attached versus 3. So they can't get as far away from each other as we could with 3 or 2 things. And we do end up with a tetrahedral bond angle of 109.5 degrees. Question on that. So up until this point, as we've been talking about, when you look at the Lewis structure, there's no dots on the central atom. So typically speaking, when you draw a Lewis structure and you have no dots on the central atom, which means you have no lone pairs, both the electron pair geometry name and the molecular geometry name will be exactly the same. And that's because, as I mentioned, as those electrons move, so do the atoms, and they end up in the same geometry. Now, when we start to introduce some non-bonding electrons or dots on the central atom, we start to get some different molecular geometries. So out of these 2 names, the name that will start to change is actually the molecular geometry. And the reason for that is the electron pair geometry stays the same because there's still the same number of electron pairs, but one of them is now not a bonding pair of electrons. They're a non-bonding pair of electrons. That means that they do not have an atom present, and that gives all the other atoms and electrons a little bit more room and space to kind of move a little bit further than they could if there was another atom sort of stuck in the way. So what it affects in terms of the names is only the molecular geometry name is the only name that changes. The electron pair geometry name will still be based on how many electron pairs there are. Now, the other factor that comes into this is the types of electrons that you have present and the interactions that you have present when you start to have non-bonding electrons. So there's sort of a worse situation, good situation-ish. The good situation is sort of what we were just talking about, and that's like bonding electrons near bonding electrons. So in your Lewis structure, lines near lines, that's like okay, not too bad in terms of wanting to get away from each other. The next worst thing that could happen is you could get some non-bonding electrons, which are dots near some lines. That's a situation where those dots now want to get a lot further away from those other electrons. So we're going to get a little bit more of a difference in the geometry, a little bit more bending, if you want to think about it that way, and some space happening, and we'll get a different name in terms of the molecular geometry. The worst situation you could have is these non-bonding electrons near non-bonding electrons. They absolutely do not want to be near each other. They're going to go as far in the opposite direction as possible. And remember that as they try to do that and get as far away as possible, we still may have things that have bonds, right? And so those guys also got to kind of move as those electrons move, and that's going to cause the shape of the molecule to change as well. So this is really the reason why we start to see the molecular geometry name change, because of those non-bonding electrons not being there. It actually provides a little bit extra room for things to move, and the interaction is even worse, so they try to get further away from each other as possible. So let's take a look at some of these. We'll take a look at sulfur dioxide, which I think we drew the other day. And if you draw it, it will look something like this. And once again here, we're only going to be concerned with our central atom. And we're going to look at the number of electron pairs. How many electron pairs does this guy have? It has one there, and how many here? It has only one. So this is a situation where our double bond only counts as one. So it has 3 electron pairs, or the steric number would be 3 in this case, if you were to draw this. Yeah. Number of bonds in this case would be 1 there. And once again, our double bond only counts as a single bond, and it would have only 2 electron pairs. So in this situation, we got some bonding electrons near bonding electrons, but we also have some non-bonding electrons near bonding electrons, which is not good as well. So in terms of the electron pair geometry name, it is still based on the fact that we have 3 electron pairs. So just like we saw earlier, that would mean it has a name of trigonal planar. But as I mentioned before, what's going to happen is these non-bonding electrons are going to try to go away, and that's going to cause these guys to try to get away from each other. But remember that these oxygens will start to move sort of down, but they also have to sort of maintain a little distance from each other because that's going to get the bonding electrons and bonding electrons near each other. So they can't just get right on top of each other. They got to kind of keep some space between them. And what ends up happening is we get a geometry, which I'm going to go with for us in here for lecture, I'm going to call angular. And the reason I'm going to call that angular is because of the bond angle associated with it. I will say some people will call it bent. Some people will call it bent angular. But we're going to use angular for this arrangement of 3 electron pairs and 2 bonds. The bond angle is always based off of, by the way, the bond angle is always based on the electron pairs that are there, electron pair geometry. So it actually will be a little less than 120 degrees. Again, it's going to be a little less because it doesn't have that third bond there. So it's got that little extra movement that it could do. So it's going to be a little less than what we see with that trigonal planar that we saw with 3 electron pairs and 3 bonds. Any questions on that one there? The next example would be something like NH3, which is ammonia. And again, we're going to focus in on the central atom always, and the number of electron pairs, and the number of bonds. So number of electron pairs in this case is going to be 1, 2, 3, and 4. Again, doesn't matter if you're counting dots, lines, double bonds, triple bonds. Everybody counts as 1. So that is 4. And our number of bonds would be 1, 2, and 3, which would be 3. Something with 4 electron pairs still going to give us an electron pair geometry of what is known as tetrahedral. But now what's going to happen in this case is we have these non-bonding electrons up here, which again wants to kind of get away from these guys. These guys has to maintain some distance, and we do have that extra bond in the middle. So again, they can't get too close to each other. And we do get a molecular geometry name of trigonal pyramid. And that is because it kind of makes a triangle and kind of makes a pyramidal shape there on the bottom as you kind of come through it. Now, this is a good time to talk about 2 names that we just talked about. This is trigonal pyramid. If we have, as we saw earlier, 3 electron pairs and 3 bonds, that is trigonal planar in terms of its molecular geometry, right? And you do need to specify which one you're talking about. You should not write trigonal unless you would like me to choose, and I'm going to choose with an X, so you don't want that, yes? Or my other favorite one, which is I'm super confident coming into my writing here of trigonal. I'm still confident with the P, and then I'm a little less confident on the rest of it. That is clearly trigonal plane pyramid. Which one is it? Plane pyramid? I'm not sure. So make sure that you really choose correctly. They are different. They do mean different things in terms of their geometries and also in terms of their bond angle. This bond angle, by the way, would be less than 109.5 degrees, which is our tetrahedral bond angle. It's about $1.06, I think, or something like that, 105, something in that ballpark, is the bond angle for NH3 in this particular case. The next geometry that you need to know, and the good thing is the last one for our class is good. When you go to 1A, there's a ton of geometries they add on to this list for your expanded octets and stuff like that. It's something like we see here in water. And once again, we're going to look at the central atom. We're going to do our number of electron pairs and our number of bonds. And we got 1, 2, 3, and 4 electron pairs. We have in this case only 2 bonds. Once again, our 4 electron pairs tells us our electron pair geometry name is going to be tetrahedral. This case here with water has all the worst things that can happen in a molecule. It has bonding electrons near bonding. It has non-bonding near bonding. And it has the worst interaction, which is non-bonding electrons near non-bonding electrons. So what happens in this particular case is those electrons here decide to go as far away as possible. And it also wants to keep away from the hydrogens, which causes the hydrogens to sort of bend down. And again, these hydrogens got to keep a little bit of room between them. And that means what happens in terms of water is we end up with a molecular geometry known as bent or V-shaped. And this is why we're going to use angular for the other one, and we're going to use bent or V-shaped for this arrangement. The bond angle is actually different as well. The bond angle there is also less than 109.5 degrees, about a 103-ish or so in the case of water. So it's significantly kind of lower in terms of the bond angle. This again is probably the easiest way to do geometry is just to make a table. I think I put a table up on Canvas as well that talks about geometry and molecular polarity. I think it's with the lecture notes, if I'm not mistaken. Somewhere in there it says like geometry and polarity PDF or something like that. And just to memorize electron pairs, bonds, and the geometries that go with it. And that's probably the best way to sort of learn the geometry. Any questions on that there? Here's a couple of tables from your book that goes over the geometries. You are going to be responsible for both the electron pair geometry name and the molecular geometry name. And also they do want you to know the bond angles. So you will be responsible for the bond angles as well. So if we just think about, some of the stuff that maybe we have drawn before, maybe I'll do it here. We had something like this, I think we drew the other day. We drew this guy. We drew this guy, I think. We also drew, I'll draw this one maybe. We drew this guy that we'll talk about here maybe. And we also, I think, looked at this guy here. So when you look at something like this, again, electron pairs and bonds is what you want to look at. So when we look at the central atom here, that is 4 electron pairs, right? And 2 bonds, which means the electron pair geometry is based off of the 4, which is tetrahedral. And because of the 2 bonds, it would have a geometry of bent or V-shaped. This is going to be just straight up linear, right? Because it's only 2 things there. So that's a diatomic molecule. This one would have how many electron pairs? 2. Yep. Each double bond only counts as 1, right? And bonds would also be 2 as well, right? So 1 electron pair, 2 electron pairs, 1 bond, 2 bonds. So that puts us right here at this situation where the electron pair geometry name would be linear and the molecular geometry name would also be linear, both the same name because they're both bonding electrons, right? So that's no dots, same name. This guy right here would have how many electron pairs? It would have 1, 2, and 3, right? Double bond counts as only 1. Number of bonds would also be 1, 2, and 3. They all would count as 1. So that would put us right here, right? This is going to be trigonal planar for the electron pair geometry, and the molecular geometry will be the same since there's no dots. Question on how to do that there. So what about this guy here? So let's take a look at this guy maybe and see. Maybe I'll do it here. So if I redraw this guy that I think we drew the other day, which is our nitric acid, when we actually look at this particular guy, it has 2 central atoms, and you can do geometry for things that have multiple central atoms. You actually just do it for each central atom separately. So in this case, the nitrogen would be considered a central atom, and so would the oxygen be considered a central atom. So if you were going to do the geometry for this thing first, the first thing you would want to do is kind of like put your hand over the oxygen side there and just look at the nitrogen. By the way, the line coming into the nitrogen still counts. So when we look at the nitrogen, it has number of electron pairs is how many? Would be 3 in this case. 1, 2, and 3. And the number of bonds would be 3 as well. 1, 2, and 3. So the molecular geometry for this guy is 3 electron pairs and 3 bonds, which is trigonal planar. The electron pair geometry would also be trigonal planar, right? Because there's no dots on it, so it's the same name. Now, once you do that, what you would do is basically move your hand and cover the other side, the nitrogen side, and look at the oxygen. So you would just kind of put your hand over this side. Once again, that line coming in is going to count for the oxygen as well. And if you look at the oxygen, the number of electron pairs is going to be 1, 2, 3, and 4 with that guy coming in. And the number of bonds in this case would be 1 and 2, which means the molecular geometry for the oxygen is 4 electron pairs and 2 bonds, which is our bent, our V-shaped in this case. The electron pair geometry for the oxygen would be tetrahedral because it has 4 electron pairs now. So if you were to build this model later, which you're not going to, but if you did, you would see something like this where, the oxygen would kind of come this way. And for the nitrogen part, it would make that triangle shape. But what would happen with the hydrogen on the back end is it would jettison up that way. And when we look at the oxygen part, what we end up with is something that looks like this. That looks like the letter V, which is why it's sometimes referred to as V-shaped, yeah? Because it could make a V, and you actually see both of those geometries sort of happening in that particular case. Any questions on if you have multiple central atoms? So really just kind of put your hand over one half of it, do the geometry, move to the other half, and do the geometry for the other central atom. Any questions on geometry, molecular geometry, electron pair geometry? You do need to know it, obviously, like everything else in those classes, I suppose, yeah. All right, then let's finish up talking about dipole moments. And clearly I littered all over this slide, so let me erase it. Try that again. All right. So the last thing we're going to talk about is molecular polarity. And this is whether or not the molecule as a whole is going to be polar or nonpolar. So if you remember earlier, we talked about bond polarity. And that is where we use the difference in electronegativity values. And that's like the 0 to 0.4, the above 0.4 to 2. And we drew those arrows, right? Those little bond dipole arrows where it points to the more negative side of the bond, and that's to the more positive side of the bond. When you do have a polar molecule, what that means is taking into account all the bonds that are present in that molecule, there is unequal sharing as a whole of those electrons over the entire molecule. And what that creates is a side of that molecule that's more positive and a side that's more negative. And that means that it has what is referred to as a dipole moment. To further complicate things, the way we represent dipole moments is that exact same arrow is used to represent a dipole moment. And it means the same thing as it did there, negative side on that side, positive side on that side. So we could sometimes use those arrows to represent a dipole moment, which means the molecule itself will have a more negative side versus a positive side. So polar molecules are the only ones that have dipole moments and have that sort of overall separation of charge of positive and negative. If you have a nonpolar molecule, what that means is overall with all the bonds that are present, the electrons are being shared equally. So there is no side that's more positive. There's no side that's more negative. It's almost like a neutral molecule, if you want to think about it that way, because the electrons are being shared equally in this particular case. The one and only place where bond polarity and molecular polarity, which is what they're asking for on your activity, by the way, where it says polarity, they're asking for molecular polarity, is when you're dealing with this type of molecules, which are diatomic molecules. So the only place where they kind of cross over, that the bond polarity and the molecular polarity will be the exact same thing, is if you're dealing with a dipolar molecule. So if you have a homonuclear dipolar diatomic molecule, that's a fancy way of saying you have two of the same elements present. So like H2, O2, N2, right? So the deal with each of these, right, is if we were looking at the bond polarity and we did the difference in electronegativity of each of these guys, we should end up, right, with a difference of 0 because they're each the same element, right? So we take the value of hydrogen minus the value of hydrogen, 2.1 minus 2.1, we get 0, right? Now, what that means is each of these things have non-polar bonds, right? So that bond that we see here, that double bond that we see here, that triple bond that we see here, those are all considered nonpolar bonds, equal sharing of electrons. In each of these cases, how many total bonds are there in these molecules? Each one has a total of how many bonds? 1, which means if that one bond is nonpolar, it would make sense that the entire molecule would also have to be nonpolar because that is the only bond present. So this would all be a nonpolar molecule because the only bond present is nonpolar. So that makes it pretty simple to determine. You go, that bond is nonpolar, that molecule should be nonpolar. That is why things like Cl2, right, Br2, I2, that you did the experiment the other week, they ended up with the hexane or heptane, whichever one you use there, because heptane is nonpolar. Those guys are nonpolar, right? Because they are all the same bond. And that's why they mixed together and they were in the top layer of that experiment that you did. Heteronuclear diatomic molecules means we got different things present, like HCl, HF. In this case, as we talked about, this will have a polar bond, right? Heading towards the fluorine because it's more electronegative, which means each of these guys will have polar bonds. And once again, because it is only a diatomic molecule present and there's only one bond present, and that one bond is polar, then this molecule has to be a polar molecule as well. So they are the easiest ones to determine diatomic molecules. If you have a polar bond, then you have a polar molecule. If you have a nonpolar bond, you have a nonpolar molecule. Again, when you're dealing with only two atoms, diatomic molecules. By the way, this bond, this little thing that we drew here would be referred to as the dipole moment in this case. And that means that the fluorine side of this molecule is more negative. The hydrogen side is more positive. And again, that arrow represents the same thing. So those two on the bottom would have dipole moments. The guy up on top would not have a dipole moment. Any questions on that? Once again, it would be nice if everything was that simple, but of course, it's chemistry, so no. So when we get to 3 or more atoms, you actually have to look at two things to determine whether or not the molecule will be polar or not. You have to start out with, are there polar bonds? So clearly, I suppose if the answer is no, there are no polar bonds, then the molecule should probably be nonpolar. So that's, it's pretty straightforward. If there happens to be polar bonds, the next thing that you have to look at is the molecular geometry or the shape of it. So let's take the classic example of this, which is our friend carbon dioxide that we drew earlier. Now, when I look at carbon dioxide, is it polar or nonpolar? What do we think? It is polar, and that is, we could find out because we look at the periodic table. There's multiple ones in here, I suppose. we look at the periodic table, carbon and oxygen are in the same period of the periodic table, right? Looks like this. Oxygen is further to the right, which means it should be more electronegative. And as we talked about before, you could sometimes, like in this case, use the general trend to figure out that it should be polar because they're in the same period on the periodic table. And it would create polar bonds. So we would have a polar bond heading towards the more electronegative oxygen. We would also have a polar bond heading towards the electronegative oxygen on the other side. So this molecule here has polar bonds. So you may say to yourself, probably makes sense that it's a polar molecule. But we do need to think about what the geometry of this is. The geometry of this guy, when we look at the number of electron pairs, is 2. And the number of bonds is also going to be 2, which means the molecular geometry is going to be linear in this case. It's basically a straight line. So if I take my molecule, which is a straight line like my pen here, and I have oxygen on this side pulling, and then I have oxygen on the other side pulling, and I'm really pulling in opposite directions really hard, my pen is going anywhere, or is it staying in one place? My pen is not going anywhere, right? It is pretty much staying in one place. And that's basically because I have equal and opposite guys pulling, like on a rope and tug of war, right? We've got equal pulling on both sides. The little flag in the middle is just going to kind of stay there. It's not going to go one way or the other. They're going to cancel each other out. And because that is the case with the geometry here, although this does have polar bonds, this is actually going to be a nonpolar molecule because those bond dipoles will cancel each other out. Dare I say these are vectors from physics? Vectors, I think, have direction and magnitude. I fell asleep after that part, but I woke up long enough to remember that in certain cases, vectors add to each other, right? And in certain cases, they cancel each other out. The cases where they cancel each other out is where they go equal and opposite directions, right? Like pulling on the rope. Or if they actually head straight at each other, right? Kind of like if you had a swinging door and you had two people on opposite sides of the door pushing equally, door is never going to open, right? And they kind of cancel each other out. So when you have a situation based on the geometry that you see these bond dipoles, which are technically vectors, heading in equal and opposite directions, they will cancel each other out, and you will get this kind of non-polar molecule, even though it does have polar bonds. So it's a really good example to demonstrate that you could definitely have polar bonds, but still have a non-polar molecule because of the geometry. Now, if we take something like our friend water here, a little H2O action happening. The bond between hydrogen and oxygen is also polar, with oxygen being more electronegative heading in this direction and heading in this direction. So water here does have polar bonds. Now, when we look at the shape of water, which we did earlier, it has 4 electron pairs and 2 bonds, which means it has that bent or V-shaped geometry with its 4 electron pairs and 2 bonds. So what we have in this case is something like this, where got kind of like a triangle of kind of bent type thing happening here. We got guys coming this way, guys coming this way, almost like they meet up there on top. Like you have a string up on top, and if you pull the string on top, right, the whole thing is going to kind of move together. And what's going to happen in this case is we will get what is referred to as a net dipole moment heading in this direction, where the oxygen side of water is more negative, the hydrogen side of water is more positive because of this unequal sharing of electron, and that's what's known as the dipole moment. Yeah. And this would be a polar molecule. I vaguely remember waking up for a 3rd time in that class, and I think you do something like this in case you're curious, a little head to tail type action, and then you join those two for the net dipole as they come together. Then I clearly dropped a class after that because there was too much sleeping happening. Any questions on that there? So clearly everybody wants to draw vectors. Nobody wants to draw vectors. Nobody wants to do any of that. Otherwise, you'd be in a physics class, right? And you're not in a physics class. So you're in a chemistry class. So there must be a quick way to do it without drawing vectors. And the answer is there is a quick way to do it without drawing vectors. And you'll probably be right most of the time. 99.99% of the time, you'll probably be right, I would assume. So there are certain geometries, and we're talking about molecular geometries here, that are what are sometimes referred to as being symmetrical. And in the case of you guys, you really only have two geometries that are considered symmetrical. That is your molecular geometry, which is trigonal planar, and your molecular geometry of tetrahedral. And if you remember, if you look at the Lewis structure, when you draw these two guys, either one of these guys, and you have these geometries, you will have no lone pairs on the central atom. So, lack of a better description, no dots on the central atom, basically, when you draw your Lewis structure. And if you have no dots on that central atom and all the outside atoms are the same element, that means what's going to happen is everybody's going to end up being equal and opposite of each other. They're all going to cancel each other out. You're going to end up with a nonpolar molecule. That's that phone right there. It's like soothing music. Oh man. All right. That didn't seem like the dangerous music of like stop, drop, and roll or anything like that. Or, by the way, I use that for all emergencies. Stop, drop, and roll. Earthquakes works well because they're rolling as well. All right. So draw this Lewis structure. You got no dots on that central atom. So if we lay something up like this, hypothetically speaking, maybe the first one on your assignment there tonight. I don't know. When we look at this, it's got some polar bonds heading towards the fluorine. So this guy definitely has polar bonds. But frankly, I don't even have to worry about that because when I look at the central atom, I see no dots there. I see all the elements on the outside are the same. I know pretty much that's going to be a nonpolar molecule just because of that. Now, what would happen if I took one of those fluorines and I swapped it out for a hydrogen? Let's say we swapped one of those guys out for hydrogen. We would still have our polar bonds heading this way towards these guys, right? The carbon-hydrogen bond is nonpolar, right? Is that 0.4 difference? At best, it's actually heading maybe a little bit towards the carbon, not so much. But what we now have in this case is we got three guys on this side, really, pulling this way, right? And we got nobody over there going in the equal opposite direction, which means we're going to have like a tug of war, three people pulling on the rope on one way, one guy hanging on for life on the other way. He's going to end up in the mud, right? If you have the mud where the thing is in between. So it's going to go from a nonpolar molecule like it was on the left to now a polar molecule because we're going to have unequal sharing of electrons. So this guy over here would be a polar molecule. So if you draw a Lewis structure and you see no dots on the central atom and everything on the outside is the exact same element, you're probably a pretty safe bet to go nonpolar molecule. If you draw a Lewis structure and you have no dots on the central atom, everybody on the outside is not the same element, it's probably a pretty safe bet to write polar, and it's going to be a polar molecule. Questions on that? Now, there's also unsymmetrical geometries. So if you look at unsymmetrical geometries, that for you guys would be you got angular. I'm having trouble spelling it. Angular, bent, or V-shaped. And trigonal pyramid. Hey, there we go. So what all these have in common is when you draw the central atom, you have lone pairs. Or to be very crude about it, there's dots there when you draw your Lewis structure on the central atom. And if all the outside atoms are the same, it will be a polar molecule. So you can really super quickly assign molecular polarity by as simple as going, I see dots or I don't see dots. And you will probably be right in almost all cases by doing so. So if we look at some examples for some of the things that we drew, by the way, that does only leave you one geometry that you do have to worry about, which is linear. And the linear one is pretty straightforward. If you have a linear geometry, like we had with the CO2, they're going opposite, they will cancel. If you have a linear geometry where they're heading right at each other, it will be nonpolar. But it is possible to have a linear geometry where all the arrows are pointing in the same direction. And that'll be like everybody's pulling on just one way, and it would become polar. So that would be the only one you have to sort of really kind of think about, which way are those arrows pointing, is linear. But since it's a straight line, you could just think of it like a rope, and that's a good way to kind of figure it out. So if we look at some of the stuff that we drew, I don't know what we drew. We drew this. I'm not going to draw all the electrons, except for the central atom, obviously. We have that we drew. Obviously, we did the CO2. We saw this guy, I think. We saw this guy. I think we drew this guy here. Right. I think that's good. All right, so if we're just going to do this really quickly, right? Should this one be polar or nonpolar? I look at the central atom. Are there dots? Are they all the same? So it's going to be nonpolar, right? No dots, all the same, nonpolar molecule, right? Here I see dots, yes? Everything on the outside is the same. Polar or nonpolar? Polar. Dots with all the same, polar. I see dots. Everything on the outside is the same. Going to be polar. I see no dots. Everybody on the outside is the same. It's going to be nonpolar. I see this. Polar or nonpolar? It is going to be polar. No dots, but they're not all the same, right? So it's going to be polar in this case. That's as quick as you could do molecular polarity and be right. Yeah. Any questions on how to do that? So I would say that's probably the easier way to do it, to be truthfully honest with you. And that's the way I would do it. And I believe that should wrap up this chapter, which is chapter 12. That's what we were just talking about with the CO2. Like I said before, I'll double check, but I believe up on Canvas, there's a file that says geometry and polarity. And if you click on that, I made a chart of all the geometries, and I kind of talked about the symmetrical, unsymmetrical, and the kind of the quick way you could kind of do geometry, and that's a good thing to reference. So in case later on in lab you want to look at it, it should be up there as well. We're going to roll to chapter 5, talk a little bit about naming for what's left here. Just give me a second to find. Okay, so we're going to talk about nomenclature, which is chapter 5 here. So this is, I guess, a fancy way of saying naming. I'm not really sure how fancy that is, but is a fancy way of saying naming. We're going to talk about how to name the two types of compounds that we've been talking about with bonding, which is ionic, which obviously is our metal and non-metal. And obviously, as we've talked about, electrons being transferred, creating ions, right? Our cations, which are positive, our anions, which are negative. And we'll also talk about molecular, or sometimes people call it covalent, which is basically two nonmetals where we share electrons, right? So before we get going into this, a reminder that when we look at the periodic table, everybody in group 1 makes a +1 charge. Everybody in group 2 makes a +2 charge. Coming over here to group 3, which is typically aluminum, will make a +3 charge. We have sort of our staircase coming through there. We kind of skip group 4. Group 5, which is our nonmetals above the staircase, will make a -3. Group 6 will make a -2. And really small in there, group 7 will be a -1 in this case. Our transition metals typically can make a variable positive charge, so it does depend on the situation as to what type of charge they could have. But there are 3 transition metals that have fixed charges. which is zinc and cadmium. They will always form a +2 charge and hang a left there by cadmium, and silver will always form a +1 charge. So these guys have fixed positive charges, and it's important to know that as you go through naming. We talked about it, I think, at the end of chapter 4, if I'm not mistaken. But remember that whenever we put something together that has a positive charge and a negative charge, right, the overall charge needs to equal 0, right? And that means that we would need something like 2 of these guys to have a proper formula of MgCl2. So when you write a compound for an ionic compound, it should never have a charge, but it is made up of 2 things that are charged, which is this would be the cation formula. And by the way, this would be the anion formula here, not Cl2 minus, no such thing. So it is Cl minus. So when you write the formula for the anion, you want to make sure that you write it correctly. So that's also really important to remember as we go through this. So let's talk a little bit about some of these things. Certain things do go by common names. And for example, it is not a trick question. When you see it on the exam, it is water. So put water next to H2O. Although I do enjoy the variable answers that people put for that, like some dihydrogen monoxide, because nobody wants a refreshing glass of dihydrogen monoxide. Probably why they don't call it that, right? They'd rather have water. NH3 is ammonia, which shouldn't be confused later on with a polyatomic ion, which looks very similar to that. And CH4 is methane. That's the simplest organic molecule that you could have. So if you see any of those 3, those are the names you really should roll through: water, ammonia, and methane for those guys. So when we talk about naming compounds, there are, again, 2 classes, as I just mentioned: metal and nonmetals, which are ionic, which are named differently than how we name our covalent bonded guys, where we have our 2 nonmetals together. So there are certain rules that go with the type of bond or compound that you have going on. And that's why, as we'll talk about, probably the first thing that you really should do when you're looking at something to give a name, if you have the formula, is to try to identify what type of elements you're dealing with. Are you dealing with a metal and a nonmetal? Are you dealing with 2 nonmetals? And that will help you focus in on sort of the proper way to name these things. So let's get into sort of how we go about this and talk about type 1 and type 2, which are types of ionic compounds. The cation always comes first. So when you write the formula or you name an ionic compound, we always do the cation first, positive guy, followed by the negative guy. So when you write the formula, positive guy first, negative guy second. When you name it, positive guy first, negative guy second. Now, when you have just the ions by themselves, we basically name them a certain way. So for example, if you had just positive cations like H plus, Na plus, Ca2 plus, we simply just use the whole name of the element. So H is hydrogen. This would be known as the hydrogen ion. Na is sodium. This would be the sodium ion. Ca is calcium. This would be the calcium ion. When we have anions, which are negatively charged ions, like H minus, Cl minus, O2 minus, we actually replace the last part of the name, like we might have talked about in that chapter as well, and we do add IDE to the end of it. So H minus is actually the hydride ion. Cl minus would go from chlorine to chloride ion. Oxygen would go from oxygen to the oxide ion. Hydrogen, as you can see there, is one of the only elements that could kind of go both ways. It could be positive and it could also be negative. Hydrogen will most of the time probably be positive, but if you have hydrogen that comes after a metal, it will actually be the negative version of hydrogen. So it does happen, but it has to kind of follow a metal for it to be negatively charged. So type 1 and type 2 compounds, which are ionic. So these are both ionic type of compounds, which means we have a metal and a non-metal together. And I could honestly say that when you are naming and you have a metal that is present, that is the most important thing to look at. So that is the one thing that you should focus on in terms of how you should go about naming it. So what is a type 1 metal? It is what we see here. A type 1 metal has a fixed positive charge, and that is our group 1, 2, and 3 are zinc, cadmium, and silver. And what that means is it doesn't matter who they're bound to, how many they're bound to. Sodium will never be anything other than a +1 charge. So it is like fixed. It doesn't matter the situation. There's always a charge. And that is different than type 2 compounds. Type 2 compounds are typically our transition metals, are just to the right on the periodic table, kind of below the staircase. So there's our transition metals, kind of in this region below the staircase, where we have things like lead, tin, bismuth, antimony, those type of guys. So just to the right there of the periodic table. These guys could have variable charges. So as you see there, chromium in certain cases could be a +2 or +3 charge. Copper could be a +1, +2 charge. Iron, for example, could be a +2, +3. Lead can be like +2 or +4. So it does depend on the situation. And because of that, type 1 and type 2, there's a slight difference in how we name a type 1 compound versus a type 2 compound. So let's take a look here. That's a table that talks about the individual ions. By the way, you can see here all the positive ions just use the name, and all the negative ions have the IDE. Also really important is if you're asked to write the formula for an ion, it does need to have the charges. Otherwise, it's not an ion. So if you're asked to write the formula for the sodium ion, it should be Na plus, not just Na. So you have to put the charge in if you do write the formula for an ion. So let's get into type 1 and how we go about it. So type 1 is pretty straightforward. You basically will use the whole name of the metal, and the non-metal, you'll drop the last part of the name and you'll add a little IDE action. So here's the deal. Go a little MgCl2. I look at this thing and I look and I first see that is a metal. That is a non-metal. So what that tells me is this guy is ionic. And once I see a metal is present, I want to look at the metal. I want to look at the periodic table, and I see that that metal is in group number 2, which means it has a fixed positive charge of +2, and that means this is a type 1 compound. Once you determine that this is a type 1 compound, you don't have to figure out anything else. All you have to do is just follow what it says. So the whole name of the first element there would be magnesium, and chlorine would become chloride, IDE. So this would be magnesium chloride. Let me answer the question that you have, which is, what about the 2? Shouldn't I lay up a little dichloride? That sounds more chemistry-like. That only sounds like you're going to get an X if you do that, because you do not want to do that. So there is no place, I'll repeat it twice, there is no place for prefixes in ionic compounds. You never use it, although people always want to use it. They think it's more chemistry-like, I think. There's a certain place where prefixes are used, and this is not the place. So if you got a metal, you should not be using prefixes at all in this situation. The reason, obviously, the 2 is there because of what we talked about earlier. In order to balance out the +2 charge on the magnesium, we need 1 and 2 of those chloride ions, and that is what the 2 is there. So it has no effect on the name. You could have 400 chlorides. You could have 200 magnesiums. You would still just call it magnesium chloride and probably have the wrong formula, but it has no effect really on the name. Any questions on that there? So again, a reminder, as we just saw there, although when we put the metal and non-metal together, we should have no charge. it is still made up of two things with a charge. So when I look at Ki, metal, non-metal, metal is group 1, which means it's a type 1 compound. So we would roll with the whole name here, which is potassium, and iodide, IDE for the second one. That has no charge, but it is made up of a cation. If I had to write the formula, that should have a charge written with it. And the anion in this case would be I minus, right? Any questions on that there? Same thing with sodium chloride. NaCl has no charge when we put it together, but it's made up of two things that do have charges, a sodium with a +1 charge and a chloride with a -1 charge. All right, so why don't you try some here, name these guys, and also write the formulas for, let's do lithium nitride. Let's do a little barium oxide. And let's do aluminum. We'll do aluminum bromide. All right, so correct names on the left, correct formulas on the right. See what you come up with. Since we're getting to the end here, we're going to look at these. We see potassium, which is a metal. We see Cl, which is a non-metal. Once again, that metal takes the priority. Potassium is group number 1, which tells us it is a type 1 metal because it has a fixed positive charge. That's all we need to know for naming. This is going to be potassium, whole name of the metal, and IDE there for our chloride part of it. This is made up of a cation that's K plus and an anion that is Cl minus, which is why we have one of each when we put it together. This is zinc, which is a metal, sulfur, which is a non-metal. Zinc is a transition metal, but it is one of those ones that have a fixed positive charge. So it does fall under type 1. And that means that we would roll with the whole name of our metal. And this would be sulfide. This is a cation that is +2 and an anion that is -2, which again is why we have just one of each of them when we put it together in that formula. This is calcium, which is a metal. Bromine, which is a non-metal. Calcium is group number 2, has a fixed charge, which means it's type 1. This would be calcium bromide. And the one I think I didn't put up there that should be there is BaH2. It was hiding. Ba is a metal. Remember, hydrogen is actually a non-metal. Ba is group number 2, which means it has a fixed positive charge. So it's a type 1 compound, which means we could just go with the name of barium. And this would be the negative version here of hydrogen, which would be hydride. This is barium with a +2 charge and 2 of these hydrogens with a -1 charge to balance it out. Any question on any of those names? So let's do the names of the formulas here to finish it out. Lithium nitride, lithium is a metal, nitrogen is a non-metal, so that tells me it's ionic, so I need ions. I want just the basic ions for each of these things. Lithium is group 1, which is +1. Nitrogen is group 5, which is -3. So when we put this together, we need to equal 0. We need more of the lithium, right? We need 3 of the lithium. And frankly, you could just count what I just did there. 1, 2, 3. So lithium with a 3 next to it, and only 1 nitrogen. Nitrogen that way, yeah. Barium is a metal, which is +2. Oxide is oxygen, which is -2. In this case, when we put these together, +2, -2, we just need one of each to get to 0. And that would be BaO in this case. Lastly, we have aluminum, which is a metal, and bromine, which is a non-metal. And aluminum is group 3, which will have a +3 charge. Bromine is group 7, which will have a -1 charge. Again, common number there to get to 0 is 3. Means you need more of the negative guy in this case. You need 1, 2, 3 of them, and only one of those. So AlBr3. I would recommend doing it like that, thinking about balancing out to 0. Sometimes people tell you to do this blindly, just move the charge and stuff up and down. and it will work like 94% of the time. So it won't work 100% of the time. So it's best to think about it. Hang on, relax. It's a couple of minutes fast. So it's all right. To think about it in terms of getting to zero, so that everything balances out correctly.